So today's theme is going to be the nucleus and radioactive decay and kind of dealing with those ideas of what's going on here and why. We do need a new word as we come at this today. And the new word that we're going to need is the word nuclide. It's a generic word that we're going to use when I don't need to make a distinction between atom or ion. In the world of chemistry, it matters what those electrons outside are doing. It matters whether we've got an electron or whether we have an ion or have an atom. But in the world of nuclear chemistry, since we're just looking at the nucleus, it doesn't matter. So we need a generic word that says it matters what's in the nucleus, but not so much whether it's an atom or an ion. So the nuclide incorporates both atoms and ions with a certain number of protons and neutrons. Don't let that word throw you for a loop. Tuesday in our video, we encountered a radioactive decay of uranium. Uranium demonstrated one of three possible common types of radioactive decay. Radioactive decay occurs if the nuclide is somehow unstable. So we're going to look a little more closely at these types of decay. The type of decay we saw in the movie was something called alpha decay. It's the release of two protons and two neutrons from the nucleus. Since it represents two protons and two neutrons, the particle that gets emitted from the nucleus has a positive 2 charge because it's got the two protons, but it doesn't take any electrons to go with it. There are a number of symbols that get used for alpha decay. You're going to see all of them. There's the Greek letter alpha. It's kind of like a fish swimming to the left. Sometimes you will see it done with its charge, alpha 2 positive. You will see it done as a helium nucleus, because that's really what it is, the nucleus of a helium atom. And you will see it done as 4,2 helium with that positive 2 charge up there. Now, after being so incredibly meticulous through this whole class about did something have a charge or not have a charge, it seems strange that we sometimes include the charge and sometimes not. But it goes back to this idea, the idea of a nuclide. In the world of nuclear chemistry, the charge doesn't really matter very often. And so sometimes for simplicity, you're going to see us dropping those positive 2 charges there and just not worrying about them because they don't really impact anything at all. So in the movie yesterday, we started with a uranium. So here we're going to start with a uranium 233. And because it's uranium, it has 92 protons. We also need to know how many neutrons this has. So grab your calculators. We're going to do a little quick subtraction here. What do you want to subtract? So if I take the 233 and I subtract the 92, hopefully you figured out that you've got 141 neutrons there. When we watched this happen yesterday, because it was alpha decay, we lost 2 neutrons and 2 protons. So this great big rumbly nucleus that was kind of shivering and shaking because it was so unstable spit out a piece that had 2 neutrons and 2 protons. Because it has 2 protons, it's helium. We'll go ahead and put the +2 in for now, just to represent that no electrons went with it, because the fact that it doesn't have those electrons is going to be a problem eventually. If I had 141 neutrons and 2 neutrons came out, that means that I'm down to 139 neutrons left inside. And if I had 92 protons and I lost 2, I'm down to 90 inside of there. So 229, 90, and I don't have uranium anymore. I need a periodic table to figure out what I have. So dig out your periodic tables. We need to figure out what we're left with. We are left with thorium. So in that case, this is our first daughter of uranium. So uranium's daughter ends up being thorium after one step of radioactive decay. This piece over here, the alpha particle, is the nuclear radiation. It would make my radiation monitor beep. And I think this is the first really big thing to understand about radioactive decay. People think that these radiation monitors are checking to see if we have things like uranium around. That detector can't detect uranium. That detector detects what has come off of the uranium. So we essentially can't detect the presence of the uranium until it undergoes radioactive decay, emits this little alpha particle, and my detector can detect the little alpha particle. Rachel. The thorium actually ends up not having a charge, which seems strange because it has fewer protons and now it's got these electrons, but those extra electrons essentially just get picked up via chemical reaction someplace else in the world. And so we're really not going to worry about them at all. Back to this whole nuclide thing, the electrons kind of sort themselves out. But as long as we're talking about the electrons kind of sorting themselves out, that gets at why this thing can be dangerous. This thing is going out into the world as the nucleus of a helium atom, and it needs 2 electrons, and it wants those 2 electrons very badly. As the alpha particle goes out into the world, it's basically going to take 2 electrons from the first thing that it encounters. And as long as that's the air, we're just fine. But if that is some piece of your body, particularly your DNA, that loses 2 electrons, one of the things you've probably learned in biology along the way is that having the right number of electrons in the right place at the right time in your body is critically, critically important. If this particle gets inside your body and strips 2 electrons from a DNA molecule inside your body, that's when we start to have problems with radiation sickness and cancer and the types of things that radiation can cause. We're going to have to spend basically a whole day at some point talking about how does radiation hurt you and how on earth could that possibly also be helpful. But this is the piece that is dangerous. This is the piece that gets detected by the radiation monitor. Until this piece comes out of the uranium doesn't pose a significant nuclear threat. Now, uranium also happens to be toxic in the same way that lead is toxic. So I'm not proposing that we lick it. You don't want to ingest it. But from a radioactive standpoint, the uranium isn't dangerous until this piece comes out. There are lots and lots of things that undergo radioactive decay like that. But there are other ways to get the job done. The next type of radioactive decay is called beta decay. In beta decay, This one is super strange. Inside the nucleus, a neutron turns into a proton and emits an electron. Now, this is a weird thing to think about. What this is saying is that a neutron is actually a proton and electron stuck together. But if you think about it, that's a conceivable situation. Neutrons and protons weigh the same. Electrons weigh almost nothing. If you took a proton and stuck an electron to it, you'd cancel the charge back to zero and have a particle of roughly the same size. That's a neutron, a particle that's the same size as a proton but doesn't have any charge. So one way to conceive of a neutron is to imagine that it's a proton with an electron stuck on. And when beta decay happens, the neutron splits into its two pieces, one proton, one electron. So here we have a neutron turning into a proton and emitting an electron. The charge on beta decay is -1 because it's an electron. The symbol for this is going to require us assigning some symbols to our subatomic particles. For the electron, it has no mass, so it has a mass number of 0. And it's been assigned the atomic number of -1, because you'll notice the electron isn't on the periodic table, it needs an assignment. And it gets a lowercase e to represent that it's a subatomic particle, not an atom. So we can have 0 - 1e. Sometimes you'll see that negative sign. Sometimes you won't. But you're also going to see the Greek symbol, beta, and it's always going to have the minus sign because there's actually a beta positive as well. So these are possible symbols for beta decay. Carbon-14 is something that undergoes beta decay. You've heard of carbon-14 possibly from carbon-14 dating, which again, the longer we do this nuclear stuff, the more things we have to start to answer. What the heck is carbon-14 dating? How does that work? Why would we use it? A story for another day. So if we have a 14,6 carbon, it has 6 protons and 8 neutrons. If this thing undergoes beta decay, it's going to turn a neutron into a proton. So that means that we're going to have the same number of particles in the nucleus when we get done, 8 of them, except that a neutron turned into a proton. So now, gotta do our neutron count and our proton count. If we change a neutron into a proton, this goes down by 1, 7. This comes up by 1, 7. But the total number of particles in the nucleus stays the same. So we have 14 there. And now 7 of them are protons. We just turned carbon into nitrogen. And in order to do this, we have to give off a beta particle. And a beta particle contains 0 - 1e, no neutrons, and no protons. So we haven't gotten rid of anything in the nucleus. We just traded a neutron for a proton. The other possibility is the reverse of this situation. Positron decay. This one takes a neutron and turns it into a proton. We can go the other way. Positron decay is when a proton in the nucleus turns into a neutron and releases a high-speed positron. So this requires a different envisioning. That of a proton being a neutron with a massless positive charge. So over here, we have the introduction of something new. a positron. Literally a positive electron, a massless positive charge. You just met your first piece of antimatter. A positron is the electron's perfect opposite. If a positron and an electron meet together, they simply both vanish. They're perfectly opposite. If you and anti-you were to crash into one another in the hall of Nina High School, you would simply both be gone. You're perfectly opposite of one another. You annihilate one another. End of story. You disappear in a poof of energy, and that's it. You're gone. That's what the positron is. It's an electron's perfect opposite. If it runs into an electron, poof, they're both gone. Well, that's why it's nuclear radiation, because if it hits an electron in your body, poof, your electron is gone. And we just talked about, from a biological standpoint, why having the right number of electrons in the right place at the right time is important. And so this is dangerous because it can destroy the matter in your body. So the positron in this case is the nuclear radiation. I guess we should go back a page here and label the nuclear radiation on the previous page as well. In our previous situation, the nuclear radiation was this piece. Because it's an electron that can be added to a situation where we don't need it. Notice in every case, the nuclear radiation is not the element that's radioactive. It's the piece that comes off of the element that's radioactive. So our positron has a charge of +1. Its symbol is the perfect opposite of the electron. Our positron here has the symbol 0,1e, or 0,1e with a positive sign, or since it's opposite of beta decay, we often just give it the symbol beta positive. For this one example, we're going to use a different isotope of carbon. We're going to use carbon 11. It's carbon, so it has 6 protons. (11 minus 6 is 5 neutrons. And in this case, a proton turns into a neutron. So we lose a proton, we gain a neutron, but we still have 11 total particles in the nucleus, except now we have element 5. We get some boron. We didn't change the total number of protons or neutrons, or we didn't emit any protons or neutrons. And we get ourselves to that point. Those are your 3 big types of radiation that happen when things undergo radioactive decay. So you can change an element, but you only have 3 choices. Lose 2 protons, lose 2 neutrons. Change a neutron into a proton. Change a proton into a neutron. That's it. That's the sum total of all the possibilities here. Now, there's some other factor here that also accounts for a release of energy. The release of energy that occurs along with alpha, beta, and positron decay is called gamma decay. This is nothing but energy, and it's given off as the nucleus rearranges. It often goes with other types of decay. It has no charge. Its symbol is gamma, which is sometimes a 0,0 gamma to represent no proton, no neutron, no mass, no nothing. And I think the easiest way for you to envision gamma decay is to think about, we had them last week, These big rubber balls that you sell at Walmart and the grocery store every spring. Hopefully you have all seen that giant ball thing at Walmart. It's a great big tall tower, and in there are all the different balls for children. And invariably, the kid that you're shopping with wants the one that's about 6 inches out of reach and 2 balls in to the whole entire ensemble. So you kind of reach in, you nestle your hands in, you grab the thing and you pull it out. And the whole rest of the tower goes as all the rest of the remaining playground balls settle into place because you took one out from the middle somewhere. The nucleus is no different. If you take something out, the whole thing has to kind of go and settle back into a different position. If you turn a neutron into a proton, now you might have 2 protons side by side. They're both positive, and they might need to move away from one another just a little bit. But if you take something out of a big mass of spherical objects, the remainder of them have to kind of go and settle into a new position. That is a release of energy. We call it gamma decay, and it tends to come along with alpha, beta, and positron decay. This little star right here by the iodine means metastable. Now that's a really kind of weird word that basically says this iodine came into existence because a radioactive decay happened. It's got all its protons and neutrons, but they aren't arranged properly yet. They need to go and settle into place. So in this particular case, we have a 12353 iodine. So we have 53 protons. '70 neutrons. And in gamma decay, they just go and settle into a new position. When you're done, everything's still the same. They're just arranged better. 123, 53 iodine. We lost the star because everything's arranged better. We didn't lose anything. We gave off energy. Except that energy is even more energetic than the ultraviolet rays of the sun that can give you a sunburn. Gamma radiation can penetrate into your body and sunburn the inside parts of you. And that's what makes that dangerous. A little bit of it is okay, just like a little bit of sunshine is okay. A lot of it is not okay, just like a lot of sunshine is not okay. All right, so we have 4 things that can go on here. Now we got to deal with the why. You're not going to like some of this why. The reason that you may not like some of this why is that the answer is going to be, we don't know. And not just like Dorner doesn't know, but like science as a whole, we don't know. So in the beginning, when we start talking AZX notation, people think, well, maybe I can just throw together any combination of protons and neutrons and bam, I can make a nucleus. True. Any combination of protons and neutrons makes a nucleus. But not all nuclei will hold together. Some are inherently better than others. Some stick and they stay like that forever and ever. And some don't. They don't stay forever and ever. They fall apart. So figure 1 here is a picture to represent everything we could possibly make if I let you use anywhere from 80 to 89 protons and anywhere from 120 to 129 neutrons. There are 100 different things we could make, and their AZX symbols are in all of these boxes. Of those 100 things we can make, you will get 10 good ones. And they're the ones that are kind of shaded here, but I'm going to color them because the shading isn't real dark. So maybe if you have a highlighter. You might want to color the ones that are shaded. So that's it. You can make 100 possible things. 10 of them don't fall apart entirely on their own. Now, how do we know which 10? That's just what scientists have observed. Those 10 things exist and are not radioactive. The remaining 90 of them, scientists have observed to be radioactive. Now, there's obviously not a lot of rhyme or reason to which ones are good and which ones are bad. This is just a list scientists have made. They look to see what's out there in the world, what's not radioactive. There you go. We do not have any explanation for why those 10 are okay and the remainder of them are not. So this table is just an observation that scientists have made. When you read this thing, on the y-axis, you have N, which is the number of neutrons. And on the x-axis, you have Z, which is the number of protons. Which means to get the AZX symbol in the box, you have to look at your number of protons, 80. You have to take 120 plus 80 to get 200 for your mass number. And because it has 80 protons, it's mercury. And so all the elements in the same column are going to be the same type of atom. On this chart, a shaded box is something that's stable. In other words, it's not radioactive. And an unshaded box is an unstable nuclide. Something that's radioactive. Bam, we just defined radioactive. Something is radioactive if it has a not good number of protons and neutrons. There's something wrong with the number of protons and neutrons. Something that is radioactive or an unstable nuclide will naturally undergo radioactive decay. It will eventually fall apart. The time frame over which this happens depends upon what it is, and an idea called half-life. Our goal today is going to be to learn how to read a chart to tell if something is radioactive or not. And if it's radioactive, is it positron, beta, or alpha decay? So this piece is part of a much, much bigger chart. It is this piece right up here at the top. So there's your pattern. 3 up. So I've hit the point, guys, that I actually need the glasses. There we go. I got them all. Up and over, and this little Z-shaped thing. You can probably hit your line better than I hit mine because you can actually see this stuff. this right here represents everything out there that is not radioactive. Every place that there's a dot is a stable nuclide, starting way down here and going way up there to the tippy top. Grab your Chromebooks, and I want to show you your digital version of this. This can sometimes be a little hard to see. There are two places you can find this. And I don't care how you get this open. It's now right here underneath your periodic table. I've also put it in the Unit 6 Day 2 folder because today was the day that we're talking about it. But I don't care how you go about getting it. Pop that thing out of Schoology. It takes a minute to load because it's pretty complicated. In this version of it, you can take your cursor and you can go to any one of these dots and you can point to it and it will tell you, like in this case, it's telling you that dot is at 1414. And this one is at 13 with 14 neutrons. And this dot is at 12 protons and 13 neutrons. So if you can't figure out what it is on the chart, you can always use the digital one and you can go find any one of these and you can get its exact coordinates. So let's look at some general facts about this thing. Uh-oh, DocCam's gonna put that here. Out. All right. If you were to start counting these, you would find out that there are 156 of these that have an even number of protons and an even number of neutrons. The world likes even numbers. There are 6 of these that have an odd number of protons and neutrons. And there's about 50-ish or so that have the even odd combination. All told, here on Earth, scientists have discovered that we have 156 plus 6 plus 52 plus 51, 265 stable nuclides. That's it. Of all the possible ways you can put protons and neutrons together, 265 of them get you something good. Now, the interesting thing is that statistics doesn't seem to hold here. If things were put together by literally drawing out a number of protons from one sac, a number of neutrons from another sac, and saying, I'm putting this and this together, this should end up evenly split. We should have an equal number of even, even, odd, 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 even, odd. We should end up with 265, about 66 of each variety. But we don't. Oh, wait, hang on. What will be the chances? Oh, these are all the same. Based on statistics alone, how many would you like to have both an odd number of protons, an odd number of neutrons? Should be about 66 of each. Our universe seems to favor even numbers. I'm gonna let you and your group come back to 2 and 3 here in just a second, but I need to explain how we're gonna do number 4. For number 4, we are going to try to create this situation. So we're gonna try to create figure 1, but instead of for the uppermost box, we're gonna create it for the lowermost box. But we're not gonna write all 100 of them. I only want you to put in the ones that actually have something there. So it's basically learning how to read figure 2. If I look at figure 2, the very smallest stable nuclide occurs at 1 proton and 0 neutrons. Now, if that's hard to see, it's this dot right down here. Oh, it's the bottom one, 1, 0. There actually is a dot sitting right on the baseline here. It doesn't show up real well in the photocopying. And that's what we're going to put in here. At 1 proton, 0 neutrons. So now we're getting into, please stay working document, Cam. We have 1, 1, and that's a hydrogen atom. Now, if I go back to here, there's a dot just above it. That dot has 1 proton plus 1 neutron, but it's still hydrogen. And that's it. Hydrogen has 2 stable isotopes. All other hydrogen is radioactive. Okay, next to that dot right here, there's something in this box. It has 2 protons, 1 neutron, 2 plus 1 is 3. 3, 2, helium. Morning. And it looks like helium has 1 more isotope. There's a dot here. And that's it. Helium has 2 stable isotopes. Okay, at this point, we really just need you to spend some time reading the chart and answering some of these questions here to try to make sense of the chart. So I'm going to have you move your tables and get together with your teams. Backtrack to number 2 and start working your way through using these charts to answer the questions. If you're finding the chart to be difficult to read, remember you have this digital version of it that you can pull up on your Chromebook to find the actual location of each and every one of these dots, very, very highly pinpointed. All right, so you can scoot your tables so you are close to but not in one another's spaces. At home, I'm going to make you some breakout rooms. If you run into any troubles trying to finish up this packet, just call me in and I will help you out.
I do sound it again. Z is number 2. That's number 3.
The first sense. A is